Okay, in this video we're going to talk a bit about the derivatives of inverse trigonometric functions. The inverse trig functions, we haven't talked a lot about them and their graphs. We've used them a little bit algebraically in order to solve trigonometric equations. Today we'll talk a little bit about their graphs and then lead from that into talking about their derivatives. Their derivatives will involve a combination of our work with the chain rule, as well as a bit of our work with implicit differentiation. So, first, one of our basic inverse trigonometric functions, if I have y equals inverse sine of x. Pardon the in and out focus as it adjusts. So, you might recall inverse functions are reflections of each other across the line y equals x. So if I think about inverse sine of x, a graph of it would look like a sine wave traveling along the y-axis instead of along the x-axis. There is also a picture of this a little bit better than I will draw it on page 171, figure 4.13. But it will tend to look something like this. It'll have to go back and forth between negative 1 and 1 on the x-axis. And would tend to go something like this. Now, of course, for a repeating sine wave, this would have to keep going. But then we have the problem where it's not really a function. So for our purposes, we have to restrict ourselves to this section of the graph, as is also outlined in that figure in the textbook. So our x values also have to be restricted to be between negative 1 and 1. So we have a couple of restrictions on domain and range when we talk about things like inverse sine of x, inverse cos of x, and that sort of thing. In this case, my domain would be x values between negative 1 and 1. And my range would include y values between negative pi over 2 and pi over 2. Okay, so this is our function. How do we talk about its derivative? Well, we do a little trick in that I take the sine of each side of this thing. Sine of y should equal x. Now, what I can do is use our work with implicit differentiation. I take the derivative of each side of this function with respect to x. So the derivative of sine y with respect to x is going to be cos y dy dx, and the derivative of x with respect to x is simply going to be 1. Rearranging this for dy dx, I get dy dx equals 1 over the cosine of y. Now, this doesn't turn out to be the most helpful way to think about this, so we can rearrange this with Pythagoras' theorem for trigonometry. If I have sine squared of y plus the cos squared of y, what I have is actually equal to 1. Yeesh. So, cos squared y should equal 1 minus sine squared y. Or cos y equals the square root of 1 minus sine squared y. But, if you recall from before, we have that sine y is equal to x, so I can restate this as the cosine of y is equal to root 1 minus x squared. And I can restate the derivative as dy dx equals 1 over root 1 minus x squared. With that, I have to restrict x a little bit more than I did in my domain statement above, because because obviously in this case x can't be equal to plus or minus 1. And if you see on the graph, those are places where you would have a vertical tangent. So my derivative is restricted to, and your textbook writes it out this way, absolute value of x has to be less than 1. That keeps my x values between negative 1 and 1, non-inclusive. You will notice that that is shown on the formula sheets that you've got as the derivative for inverse sine of x. The derivatives for the other inverse functions are done in a similar way, restating in terms of the original trig function and then using implicit differentiation to solve. So, I won't work through them for the rest of the inverse trig functions, but that is the basic premise for it. I'll show a couple of examples of working with these things. Yes, one other thing I'll mention as I go a bit further into examples. So, I will start with basically example 1 on page 172. Which is a straightforward means of applying what we just worked out. If you were asked to find the derivative of inverse sine of x squared with respect to x, I would treat this in a chain rule sort of fashion, but keep in mind that what is on your formula sheet talks about the derivative of inverse sine of u with respect to x. That's going to be 1 over root 1 minus u squared times du dx. So if I apply that over here, I'm going to get 1 over the square root of 1 minus x squared squared times 2x. Or, if you like, 2x over root 1 minus x to the fourth. That would be our derivative. I've just dropped a variable y in there that I didn't really describe before. I'll just put that right up there. Right. So similar formulas to these are on your formula sheet for the other inverse trig functions. Just actually be careful looking at the restrictions on the variables that are stated after them. In this case, u has to be a number between negative 1 and 1, non-inclusive. So, another example, as I clear myself up another page here. It's a very high-tech world I'm living in these days. Okay. So, I'll also take a look at example 2, which ties things back to a little bit of physics. This is example 2 on page 172. Where we are told a particle is moving along the x-axis, so its position at any time t greater than or equal to 0 is given by the function x of t is equal to inverse tangent of root t. What is the velocity of the particle when t equals 16? So effectively what we're being asked is, what is dx dt at t equals 16? Now, I do want to stress, because a lot of people will see that t equals 16, I'm going to drop it right in here for t. Don't do that, because you need to find the derivative first, leaving your variables intact, before you substitute this in. If you put 16 in for t now, all that's going to tell you is your position at 16 seconds, and not the speed, or not the velocity. So, from our formula sheet, we are told that the derivative of inverse tan u with respect to x is equal to 1 over 1 plus u squared du dx. So in this case, dx dt is going to be 1 over 1 plus root t squared times the derivative of root t with respect to time. With some simplification, this becomes 1 over 1 plus t, and the derivative of root t with respect to time would end up being 1/2 times t to the negative 1/2. I apologize for all the focus weirdness with this thing. So with some simplification, I can write that dx dt is equal to 1 over 2 root t times 1 plus t. So to finish this out, at t equals 16, I can say dx dt equals 1 over 2 times the square root of 16 times 1 plus 16. Now root 16 is 4, 2 times 4 is 8, 8 times 17 is 1856 or 136, so 1 over 136. We're not given any specific units, so we have to leave that unitless at this point. So I can say the velocity at 16 seconds, well, 16 time units, I guess, is 1 over 136. This is going to be fun. Length units per time unit, whatever those turn out to be. One last example I'm going to mention, and this is for example 4 on page 174, but I do need to mention one thing before that. So when you're dealing with the inverse of reciprocal trigonometric functions, so that would be the inverse of secant, cosecant, cotangent, and their derivatives, your calculator does not deal with those well. So I'm going to mention a few identities you can use to work out some things on your calculator if you need to. These are also listed on page 174. They're called calculator conversion identities. And they basically say that we can figure out inverse secant by doing inverse cosine of 1 over the value, inverse cotangent as pi over 2 minus inverse tangent 1 over x, and inverse cosecant of x as inverse sine of 1 over x. So, on to our example. We are asked to find equation for the line tangent to y equals inverse cotangent of x at x equals negative 1. Find tangent line at x equals negative 1. So, first we're going to need to find the point of tangency, and that's where that calculator identity is going to come in handy. Point of tangency will be at a y value of the inverse cotangent of negative 1, which I'm going to work out by using this identity as pi over 2 minus the inverse tangent of 1 over negative 1. Whether you work that out from your unit circle or with your calculator, you will end up getting a y value there of 3 pi over 4. So my point of tangency is -1 and 3 pi over 4. So at that point I'm going to need my derivative, dy dx, and if you use your formula sheets, you can see that that is simply going to be -1 over 1 plus x squared. And once again, at x equals -1, the derivative is going to end up being -1 over 1 plus 1, or -1/2. So my line, my tangent line, has a slope of -1/2 and has to pass through -1 and 3 pi over 4. Filling that in, I'll get a b value. So 3 pi over 4 equals, well, 1/2 plus b. So b would equal, some unpleasantness, 3 pi over 4 minus 2 over 4, 3 pi minus 2 over 4. This is a slightly different form than what's in your book, but it works out to be the same. Your tangent line is -1/2 x plus 3 pi minus 2 over 4. Okay, so those are the examples that I wanted to go through with everybody. I will post some questions that you can try on the Google Classroom. Feel free to leave any comments or constructive criticism there. I probably won't read the comments on the YouTube channel a whole lot. Okay, thanks everybody. Good luck.